Today's class we are going to start a new chapter, that is chapter number 12, atoms. In today's class we'll discuss about Rutherford's nuclear model of atoms. Okay, so what are the conclusions, his experimental setup, and finally the drawbacks of Rutherford's nuclear model. All those things will be discussed in this class. So let's begin this class. Okay, so let's begin this class. In this class, we are going to start a new chapter, that is chapter number 12 of your NCERT class 12 physics textbook, that is atoms. Okay, so in atoms, today our main focus will be on the discovery of nucleus, that how step by step nucleus was discovered inside atom. Initially, J.J. Thomson gave a theory. In the theory which was proposed by J.J. Thomson, it was told that it is the atom, the structure of atom is similar to plum pudding model. Plum pudding means you must have seen watermelon. What is inside watermelon? Uh, Throughout there is red colored pulp and there are seeds, black colored seeds. In the same way, it was assumed that electrons are uniformly distributed inside atom, and throughout the space, throughout the volume, there is positive charge. So there is attraction between negative charge and positive charge which attracts each other. That kind of model was given by J.J. Thomson. Later on, J.J. Thomson gave in about I guess 1904. In 1911, student of J.J. Thomson, Rutherford, carried out an experiment with the help of his two students who were uh, doing their project for their graduation. During their graduation, they were doing some project. During that project, he carried out the experiment, which we'll learn in this class, with the help of which the nucleus, location of nucleus was uh, defined to the correct extent. Okay, so we'll discuss it step by step. First of all, let us begin the class. Give the heading chapter 12, atoms. Okay, so plum pudding model totally failed because it was not possible. And when Rutherford discovered his theory, we came to know that yes, J.J. Thomson, the theory given by Thomson is not true. Okay, so in 1911, two students of Rutherford, H. Giger and Ernst Marsden, these two students of Ernst Rutherford, Ernst Rutherford, and Ernst Rutherford was none other than student of J.J. Thomson. J.J. Thomson. So these two students carried out their experiment to know the structure of atom, the nuclear structure inside atom. Okay, so now we are going to make the experimental setup, line diagram of that experimental setup to understand how nucleus was defined inside an atom. Okay, so let us make the diagram. This is a box. From this box, alpha particles are emitted out. So this is source of alpha particle. Source of alpha particle. One more thing. This source has energy of alpha particle, which is in range of 5 mega electron volt to 7.7 mega electron volt. Electron volt means 1.6 into 10 raised to power minus 19 and mega means 10 raised to 6. So this was the source from which alpha particles emit out. Now they wanted a beam of alpha particles. They don't want the alpha particle to get scattered here and there. They want the beam of alpha particle to strike the foil. Okay, so here we'll keep a foil, but to make them in a particular path, to make them go in a particular path, uh, here lead bricks are kept. Like this. Because of which the beam of alpha particle will come from this source like this, and this is alpha particles. These are lead bricks. Okay, so with the help of lead bricks, what is going to happen? They collimate alpha particles into a thin beam. Now this beam of alpha particles is going to strike the foil placed over here like this, and this foil is made up of gold, thin gold foil. Okay, after, okay, one more thing, this gold foil is so thin that there is only single layer of atom. Behind the atom there is no other atom. Okay, so this sheet is so thin that throughout the sheet there is one single layer. Behind that layer there is no atoms. Okay, so this is 10 raised to minus 6 meter to 10 raised to minus 8 meter. This is so thin. It is single layer of gold atoms. Okay, now when the alpha particles comes and they reach the gold foil, after that there are many cases. They can just go straight, no deflection, no scattering, straight, or else they can deflect at an angle, let's say 30 degree, 40 degree, 50 degree, 90 degree. They can, okay, so when they completely bounce back means the path they have traced will be completely taken up back. Okay, so these are the different possibilities which can be possible. To record those possibilities, what we need to do, we need to keep a screen wherein where we can detect that yes, here the alpha particle is obtained, here the alpha particle is present. Okay, so there is a screen like this. surrounding the plate, means foil, which is going to detect it. So see, it will be like this. Here there will be a detector. Why we are keeping a detector? Because we cannot see with our naked eye. We cannot see that yes, here there is alpha particle, here there is alpha particle. So we need to keep a detector. This is a detector, kind of microscope, which will help us to detect the position of the place of alpha particle. Okay, so where the alpha particle strikes. Okay, so we can know the angle of deflection. Okay, okay, so this is scattering angle theta, or you can say deflection angle, scattering angle. At what angle the alpha particle got detected? So this is a zinc ZNS screen. Okay, so here at this place there will be a light flash which will be detected with the help of detector. Okay, so now the setup is clear. Just we need to know where alpha particles are striking. Now the important thing are the observation, that what this detector is making the observation. Okay, so now we will look forward to the observations. Observations. Okay, so what observations were made? We need to record uh, the number of alpha particles which are obtained at a particular angle theta, which is scattering angle. Okay, why these two things are important? See, here at any place, what is the unknown thing? That how many number of alpha particles are obtained at a particular place. So that can be known by the angle theta. And what is the concentration of alpha particles at this place? We will not have uniform concentration throughout. Okay, so we need to know that what at given angle, let's say 45 degree. At 45 degree, how many number of alpha particles are present? Okay, so likewise, we will make the graph at theta is equals to 0 degree to the highest possible value is 180 degree when it is going to completely bounce back. So these possibilities are there. And here number of alpha particles, let's say 10 raised to 1, 10 raised to 2, up to let's say 10 raised to 7. Okay, exact graph has been drawn in your CBSE NCERT textbook. Here we need to just understand the observations, that what observations were made. Now this is in degrees. Okay, in degrees. Okay, so first of all, alpha particle. What is alpha particle? Alpha particle is doubly charged helium ion. Helium nucleus. Why helium nucleus? Helium has two electrons. You know that? So if I remove those two electrons, it will become doubly charged. Now there are no electrons. So there is only nucleus with two protons, two neutrons. So this helium nucleus is the beam of alpha particles. Means beam of alpha particles is made up of helium nucleus. Okay, so the charge is plus 2e and mass is nearly equal to 2 plus 2, nearly equal to 4 mu, not the exact one. Okay, so now we are going to see that how many number of uh, alpha particles are obtained at what angle. Okay, So the first observation that was made was first observation. Most of the alpha particles, that is 99.86%, went undeviated. That is theta is equals to 0 degree. Means went straight. What do you understand by this? If they went straight, means there is no deflection, no scattering. They just followed their initial path and they just reached to that screen 99.86%. This means nearly at this point. Okay, no scattering, theta is equals to 0, or you can say more nearer to this line. Okay, next observation. 0.14% of alpha particles deviate more than 1 degree. That is, theta is greater than 1 degree. 0.14% of alpha particles deviate more than 1 degree. It means there is some matter which is present inside the atom. Here we have taken gold foil. So inside the gold, atom of gold, but it is present at very small space, because throughout in rest of the space, if the alpha particle comes, it goes straight away. But there is some space inside that atom where some mass is present, which makes this alpha particle to get deviated from its original path. Next observation. 1 in 8,000 alpha particles deviate more than 90 degree. More than 90 degree. Theta greater than 90. Now there is a very small space where the mass is present. Actually, we are talking about the nucleus. We have already discovered, we know that. Okay, the nucleus is present at very small space, and that nucleus is very concentrated. The charge on that nucleus is very concentrated. That's why 1 in 8,000, that alpha particle deviates more than 90 degree. Can you understand how much concentrated and how much uh, charge it would be carrying, that nucleus? Okay, last observation. 1 in 1 in million alpha particle deviate about 180 degree. That is theta is equals to 180 degree, which means it returns back. If I say that alpha particle returns back, what does that mean? The mass, the charge inside nucleus is so strong that the alpha particle feels so much repulsion. We have learned in electrostatic force of attraction and repulsion that if two like charges uh, are kept at a place, there is the force of repulsion, that is k q1 q2 upon r square. So this force will be experienced by this alpha particle, because of which it goes straight back, moves back the same path that it traced. Okay, that's why now we will make the graph. Actually, first the dots are made and after that the graph is made. Okay, but these were a few observations which were recorded. Now, with the help of this dots and the equation, the line was made. That equation was given by Rutherford. That is, n is equals to, n means number of alpha particles. Number of alpha particles deviated at theta angle, that is n is equals to kz square upon sine raised to 4 theta by 2. Okay, so this graph is an approx graph, the line of which is traced by n is equals to kz square upon sine theta by 2 raised to 4. With the help of this equation, this line is made. Okay, so at a given angle theta, what number of alpha particles are deviated, that can be understood from this equation. Okay, so in this equation, n is equals to kz square upon sine raised to 4 theta by 2. First of all, n is number of alpha particles that you know, k is constant, theta is angle of deviation, z is atomic number of foil. Okay, k is constant, theta is angle of deviation, z is atomic number of foil. Okay, so these were the uh, things with the help of which n number of alpha particles deviated at a particular angle theta can be known. Okay, so more is the atomic number, more will be the scattering of alpha particles. Okay, so this is gold. Apart from gold, the foil can be of different materials. In that case, number of alpha particles which scatter will be different. Okay, so now based on this observations, what conclusions Rutherford has drawn, that we will understand. Okay, so now we are going to understand the model. Rutherford's nuclear model of atom. Okay, which is nothing but results or conclusions from experiment. So experiment we have already seen. Now we are going to understand that what conclusions can be drawn from that uh, experiment, that graph. Okay, so let us write down one by one conclusion. First, if you have observed that 99.86% alpha particles went straight, no deviation, can you think that yes, if there is no deviation, the majority portion inside atom is empty? Because there is no deviation means there will be nothing which is going to obstruct the alpha particle. Okay, the same way the first observation was most part of the atom is empty space, that is hollow. What is the reason? 99.86% alpha particles passes undeviated. That's why Rutherford said that yes, most part of the atom is empty space. Next observation, if there is some deviation of alpha particles means there is some mass which is present inside the atom, and if it is getting deflected, if it is getting away from it, means there is some positive charge. Positive will repel. Okay, so there is some positive charge inside atom in a very small space. The space is very small because only 0.14% alpha particles are obtained at that place. Okay, so the reason is 0.14% alpha particles which are positive in nature, doubly charged helium ion. That's why they alpha particles are getting away. They are experiencing force of repulsion. So 0.14% alpha particle deflect by more than 1 degree. Okay, next observation. Now it is known that there is some positive charge inside atom and the space is very small. The next observation tells us the positive charge inside atom is concentrated. Charge is present, but that charge is concentrated charge. Concentrated to an extremely small space. Extremely small space. Called nucleus. Okay. And he also gave that the approx size of nucleus is 10 raised to minus 15 meter. And he also gave approx size of atom 10 raised to minus 10 meter. The size of nucleus is 1 lakh times smaller than atom. Okay, because only 1 in 8,000 deflect at an angle more than 90 degree. The mass is present at very small space and that is concentrated. Okay, next observation. Number of alpha particles scattered at particular angle theta is different for different metal foils. Obviously, the equation is kz square upon sine theta by 2 raised to 4, where z is atomic number. More is the atomic number, more will be the number of alpha particles. Okay, so number of alpha particles scattered is different for different metals. Different metal foils, different metals, or you can say it can be any element. Different elements have different positive charge in nucleus. Okay, so more is the positive charge, more will be the force of repulsion. As simple as that. Okay, next and last observation. The electron are attracted by positive nucleus, but electron don't move towards nucleus. it utilizes this force as centripetal force and revolves in any circular orbits around nucleus. He said that electron is attracted by positive nucleus. Negative charge is attracted by positive charge, but the negative charge don't move towards positive charge. Earth is attracted towards sun, but it is not moving towards sun. It is moving around sun. It is revolving around sun in its fixed orbit. Okay. Similarly, electron is attracted towards atom, but it is not moving towards atom. It is revolving around it, and that is, let's say this is nucleus. This is nucleus, and this is the path of electron. Okay, so the electron moves around the nucleus, but it is not moving towards the nucleus. Here there is electrostatic force of attraction. This electrostatic force of attraction is used as centripetal force. Electrostatic force, electrostatic force is equal to centripetal force, with the help of which centripetal force helps the motion of electron in circular motion around the nucleus. Okay, so the electron which is moving around the nucleus, this electron has centripetal acceleration. Okay, so now you can understand that why electron is not attracted, because of centripetal force it is moving around the nucleus. And with the help of this equation we will further draw many other conclusions in the subsequent class, but this was the statement which was given by Rutherford. The drawback of Rutherford's experiment is, he said that it utilizes this force as centripetal force. That is true. And revolves in orbit, circular orbit. That is true. But it is not any orbit. The orbit of the electron around the nucleus is fixed. That orbit is not going to change. So this is the drawback. Okay. So we'll discuss the further studies on nucleus in the subsequent class. For now, we have concluded the Rutherford's nuclear model. So thank you all for joining this class. We'll meet soon in the next class. Till then, you can keep on learning. Goodbye and thank you all.